Welcome back. This is question 2a of Z transform. We're asked to interpret what is z to the power of n. What is z to the power of n? Well, it comes from this equation. The Z transform of xn is this expression. It takes xn and it's going to multiply by z to the power of minus n. So before we can understand what is z to the power of minus n, let's try to understand it from z to the power of n first, because z to the power of minus n is nothing but 1 over zn. So once we understood what is zn, we can understand what is z minus n. To make our life slightly easier, we are going to study for causal sequence first, n equals to 0 to infinity. So what we do is that this is n equals to 0, this is n equals to 1, and so on. And we are listing down what is z to the power of minus n. So of course, the sequence will look like z0, z minus 1, z minus 2, and so on for this sequence. And if we are studying the sequence with respect to positive power, then we are seeing it as z0, z1, z2, z3, and so on. So let's study this sequence of positive power first. To understand what is z to the power of n means, let's rewrite z in polar notation. Remember that z is a complex number, a plus jb. And of course, we can write the magnitude of this a plus jb as well as the angle. So this is the angle, omega, and this is the magnitude. Let's call the magnitude alpha, and call the angle omega. So we can bring n into this as well as n into the magnitude. Let us now see what happens for different magnitude. On the right hand side, you will see that if my magnitude of my z is 1, so implying is alpha n, but if alpha equals to 1, alpha n remains as 1 throughout. So this is like all of time, the sequence is only once. What about when alpha is greater than 0 but less than 1? That means it is between, because magnitude can only be positive number, so it can only be between 0 or 1. Now, if it is of course 0, then the whole thing goes to 0. But if it is between 0 and 1, the first value is sigma to the power of 0. This is 1. So the height is 1 for the first term. But once alpha is less than 1, then of course this is a decaying exponential sigma. Here the word causal here, because we are interested in only positive value of n in this example. Now, in the last example, my alpha is greater than 1. So if alpha is greater than 1, you will realize that the first value is still, for example, let's take an example, alpha equals to 2. So it's 2 to the power of 0 is equals to 1. This guy is 2 to the power of 1 is 2. This guy 2 to the power of 2 is 4. This guy 2 to the power of 3 is 8, and so on. So it grows exponentially when alpha is greater than 1. And for this example, I use alpha equals to 2. Now, so we understand what is the idea of the magnitude now. Whenever we have magnitude equals to 1, the sequence value remains as 1 all the time. Okay, we haven't talked about the second part of the value of ej omega yet. But let's proceed with alpha equals to greater than 1, it will grow. And alpha less than 1, it will decay. Now, for the second part of the equation, which is ej omega n, what is ej omega n? Briefly, it is a complex exponential that is going to rotate as n increases. And how fast it rotates depends on the omega, which is radian per sample unit. So in the next few slides, I'm going to draw this. So this is the real part of z. This is 0, this is 1, this is 2, this is minus 1, this is minus 2. Now this is minus j, minus 2j. This is the imaginary line. This is j, this is 2j. So where is time? So I will draw time here. So time is n equals to 1, n equals to 2, n equals to 3, and so on. So this is n. So I will now draw the complex exponential with respect to the real and the imaginary z as time increases. Let's study this sequence. So this is the sequence I'm going to show you, the real, the imaginary, and this line is time n. So why does this picture represent the complex exponential? This is a picture of a complex exponential that has amplitude 1 and 2 pi divided by 8. So 2 pi divided by 8 is equals to pi over 4, and then we have k equals to 1 here in this first example, and n will go from 0 to 7. You realize that I'm plotting a complex exponential that moves by pi over 4 radian per sample. Pi over 4 radian is 45 degrees. So at every sample, I'm going to move by 45 degrees. Let's see that if this is true. You can see that the first point here is time 0. And the second point, this is n equals to 1. This is n equals to 0. It moves by 45 degrees, or pi over 4 radian. So this is a 2D picture where you will observe this sequence from this angle. So you are a person looking into time. So the time axis now appear as a point in the middle. And you are seeing the phasor that is rotating. So you can see the n equals to 0, n equals to 1 here. And then n equals to 2 here. So by each step, as we step up n, we are moving by pi over 4, or 45 degrees. So the third point is here. So let's trace the point. N equals to 0, 1, 2, 3, 4, 5, 6, 7, and at the 8th point, it will land exactly back at this point here, where this is the origin and this is the real line value with value 1. You can also observe the problem as this figure, which is the real part versus the imaginary part, from n equals to 0 to n equals to 8. It completes one cosine for the real part in 8 samples and completes the sine for the 8th sample. So the question now is, as I am moving by pi over 4, why is the phasor looking as if it is spinning anti-clockwise? You can see it from here. As I increase from 0 to 1 step, my cosine has become smaller. My sine has become bigger. So the real part is here. Becoming smaller means it moves from this point closer to the origin. And the sine becomes bigger means I move along the vertical, it goes up. So actually it is this interpretation here, move by a little bit and goes up. So this is the real part that has become smaller as I move one step, and the imaginary goes up. Okay, so this is the thing I'm talking about. This is the real part becoming smaller and the imaginary part going up. Alright, once you can interpret this figure, you understand that this is rotating at pi over 4 radian per sample. Now, let me make the rotation faster. So, I times 2. So, if this guy is pi over 4 radian per sample, I'm going to do times 2. This is pi over 2 radian per sample. 2 times is speed. So, at each step, I'm going to move. Previously was moving by 45 degrees. Now I'm moving by 90 degrees, pi over 2. So if I do it this way, so what will you see? You will see that in the 8th sample, I have now moved along my, what do you call that? My complex exponential, move along time, and I completed 2 rounds. So previously, 8th sample, I took 1 round. Here, example, I took 2 rounds. Then of course, I can even make it spin faster. Pi over 4 times 3. So this omega now is pi over 4, 3 over 4 pi. So what's happening is that it's spinning even faster. So let's trace this line, see? So this is n equals to 0 over here, and in one step it is here, n equals to 1. Now this is very confusing, but actually this is n equals to 0 and this is n equals to 1. This is n equals to 2. This is n equals to 3. Okay, and so on and so forth. But the take-home message is that now you compare this figure, and this figure. As omega increases, we are rotating faster, completing more cycles with the given 8 samples. The detailed explanation you can read here, but it is exactly like what I have said. Now what we need to do now is to combine this magnitude and this complex exponential to the power of n. So remember that the magnitude controls whether the sequence is growing or decaying. So if alpha, the magnitude, is bigger than 1 and omega is positive, then we realize that it is rotating anti-clockwise, and as n increases, it will rotate faster and faster. Now I've drawn a blue line. Here the blue line is for a continuous version of the complex exponential. Okay, so that you don't see all the holes in between like here. Okay, so I just draw the blue line to represent the continuous time version. To get the discrete time version, of course, then you sample it at the discrete point in seconds. Now, what about when alpha equals less than 1? Then, of course, we will have a decaying exponential. So the exponential is now decaying as time increases. So we'll plot z to the power of n, where we have different magnitude and different omega. So here I have magnitude less than 1, so I am seeing a decaying complex exponential. It's rotating anti-clockwise because omega is positive. What about when omega is negative? Then he is rotating clockwise, but he's becoming smaller and smaller. If the magnitude is 1, then he is not decaying. So depending on omega, in this case positive omega, he is rotating anti-clockwise. And in this below example, again magnitude is 1, we have negative omega. Negative omega means rotating clockwise. And in the last example, because magnitude is greater than 1, he will be growing, and for both growing and depending on the omega, whether he is rotating anti-clockwise or clockwise in this below. Now we have talked about Zn, but Zn is not what we are interested in. We're interested in Z minus n. So what is Z minus n? It is nothing but 1 over Zn. So two things happen here. Okay, so let's look at if we have Z. What is Z minus n? It is 1 over this whole expression here, and we can break this expression into two parts. The magnitude part is 1 over the magnitude, and the angle becomes, because it is at the denominator, when we bring it up, it will become positive. So it's 0 minus j pi over 12 become 0 plus j pi over 12. So two things happen here. Original z is less than 1, but now 1 over less than 1 becomes bigger. So you can see that the complex exponential now is growing as n increases, even though z is less than 1. It grows because it's 1 over z. The other thing that you have to remember is that a negative omega is actually rotating clockwise, but because now it's 1 over z, it will change the direction. So he's now rotating anti-clockwise. So this is very confusing when you start. So I would strongly advise you to plot Zn first, and then you can figure out what is Z minus N. You can see the rest of this yourself and compare the patterns that I've just explained. This is the reason between Z minus N and Zn being change of the rotation, as well as the original value being decaying will now grow, and if it's growing will now decay. Alright, that's all I have for this question. Thank you.